Now we are ready to begin the discussions on mechanism design, which is the inverse thing of game theory that we have discussed so far. And to motivate this mechanism design problem, let me start with a story. I'm sure that you have heard this story in some form or the other in the past. So this is a story about one king and two women, who both of whom are claiming to be the mother of a child. And they come to the king's court and says that they want this child, and ask the king to decide who is the rightful mother of that child. And you know the rest of the story. The king says that let's cut this baby into two and give it to each of these women. And listening to this, one of the women says that I give up my claim. And then the king comes to know that this is the right mother, and gives the child to her. Now, presumably this is a nice mechanism, and you might be wondering that this is a brilliant way of deciding who is the right mother. But if you think carefully about it, you can see some of the flaws of this mechanism. So what happens if you try this mechanism once more? Will that work? So for instance, tomorrow, if another similar dispute happens and the king tries to do the same thing, and both the women give up their claim to the child, then the mechanism cannot decide which of these women to give the child to. So the problem with this particular mechanism, is that it is not committing to its rules. So initially the rule was to cut the baby and then give it to each of these women, and then later, based on the reaction of these women, it is changing its rules. So that is not the kind of mechanisms that we'll be discussing in this course. We'll be interested in mechanisms which are committed to its rules. So no matter whatever happens, you can repeat it multiple times without losing any of its properties. So think of a different mechanism. So if the king asked to both these mothers to keep some amount of wealth, whatever wealth they feel this child is worth to them, they can bid for that, and then decide in favor of the woman who bids highest, and then ask her to pay the second highest bid, that is the losing bid. So presumably the real mother must have much higher value for that kid, and it would have bid all its wealth, whatever she has for that baby, and then the other person will have much lower value, and at the end she gets that baby maybe at a much lower cost. And if you think about this mechanism, every time you run this mechanism, this will work. In the later part of this course, we'll certainly discuss about this mechanism, although not in this context, but in a different context. So the whole point of telling this story is that there are certain mechanisms which are not committing to its rules, and there are certain mechanisms which commits to its rules, and therefore it can be applied every time. And that is the kind of mechanism that we are going to discuss in this course. To summarize the idea of mechanism design, the objectives or the desired outcomes are already set, and the task is to set the rules of the game. As in this example, there are many other examples. So for instance, election, or deciding the winner of an election, that is one desired outcome. Of course, we need to decide the winner of the election based on certain objectives, and we can set the rules how we can get those objectives. Or we can do certain kind of a resource allocation. So let's say scarce resource, something like spectrum or cloud resources, that can be licensed or given away with respect to certain desirable properties. Similarly, matching students to universities. This is also a mechanism design problem. So let us formally present the general model of mechanism design. As before, we have a set of players. With the set X, we denote the set of outcomes. So for instance, in this previous example, the winner in an election is one of the outcomes. So the possible set of candidates in that election is this set of possible outcomes. Similarly, which resource should be allocated to whom? So all possible allocations are a feasible set of outcomes in this mechanism design problem. Now we are also interested in defining another set which is called the theta of I, capital theta of I. This is known as the set of private information of that agent I, and we sort of seen this kind of a situation in the case of Bayesian games. We have also defined the type set, and this actually uses the same name. So this set is called the type set, and a specific type of player I is denoted by lowercase theta of I, which belongs to this set of capital theta I. So the meaning of type is that it can actually manifest the preferences of different outcomes in different ways. So let us look at two different paradigms on which this kind of a type is defined. So the first kind of manifestation is ordinal manifestation, which means that we can only talk about the ordering over these outcomes. So the most simple example will be in the context of election or voting. Every individual agent, every voter has a complete ordering or partial ordering over the candidates that are contesting in this election. So let's say someone prefers A over B over C. That could be one way. So this particular ordering might be 1 theta of I. So that is an ordinal ordering. Notice that we are not really saying anything about how much you prefer. So in this case, we only know that A is more preferred than B and B is more preferred than C. But nothing is said about how much they are preferred. When we actually say how much that is preferred, that brings us to the cardinal setup. So what do we do in that case? We actually define something like an utility function, which takes that outcome, so one element from that set X, let's say one candidate, and based on what type you have, it is assigning a real number to that particular outcome. So you can say that, well, I have A, but I can also give certain numbers to it, let's say 10, versus for B, I can give some number like 8, and for C, maybe a very small number like 1. So these numbers will now represent my utility when each of these outcomes are chosen. So that is a cardinal. So now not only you know that A is more preferred and B is more preferred than C, you also know with what intensity you prefer them. So this kind of a model, so where your utility, so utility is just a real number which maps this X and this theta I into R. This kind of a mapping where it is only dependent on your own type, agent I's own type, this is called the private value model. We'll come back to this point, why it is private value, for the very reason that it is dependent only on your type. But it might be a little more general case where the utility is not only dependent on your type, but it can be dependent on the type of all the players. And in that situation, we call that kind of a utility model as the interdependent value model or interdependent utility model. So we'll, for the most part of this course, we'll be only interested in this independent private value model. Independent in the sense that it is only depending on its own type. Okay, so let's discuss about certain examples to understand this notation better. As we have already mentioned briefly, so in the context of voting or election, X is the set of all candidates. Now theta I is a ranking over all these candidates. So as we said, I mean A over B over C means that is theta I. So that is for the ordinal preferences. Now if you look at the single object allocation, and we have also discussed this in the past, an outcome, let's say we first decide who is going to win that object. So there is one indivisible object which is to be allocated, and it has to be allocated at a certain price. So when people are, this is the auction setup where you are actually giving away that object to one of these individuals, and you are also charging a payment. So in that case, this vector, so the outcome will be this vector A and payment vector, the tuple of these two things, and this is essentially the set of X in this case. So what is this A vector? So you can imagine that it has n components, one for each agent, and these components can take only values 0 or 1. And of course, whenever you are taking the sum over all these AIs, so all these components, that can at most be 1. That means at most one individual can be given this object. This is upper bounded by 1. That means the object might not be allocated as well. So all AIs could be equal to 0. So we'll be calling the vector A as allocation vector. Similarly, there is a payment vector, which is a very similar thing. It has also n components, but Pi, so the ith component Pi is the payment charged to I. Now, if you look at theta I is something like whenever this item goes to agent I, how much it values. So there is certain amount of monetary value associated when this object goes to that individual I. So that theta I is actually denoting that value. So therefore, we can actually think about the utility of player I in the following way. So notice that this X is nothing but this tuple of two things. So we have already defined X here. So it is just looking at, when we are defining the utility of player I, it is just looking at the ith component of that A vector and also the ith component of the payment vector, and multiplying this. Notice that this AI can be either 0 or 1, multiplying that with theta I. So that means if that agent wins, then it gets a value of theta I, and it makes a payment of Pi. So in this case, we are keeping it general, that is the payment will be the same irrespective of the winning, but in an actual mechanism, this Pi can actually be dependent on this AI, whether it wins or not. So it may charge only when the object, when the agent wins that object. Otherwise, the payment is 0. So these are two examples, one for the ordinal preference and one for the cardinal preference. So this is the example of the type set, so type of agent. Now that is the description of the mechanism from the agent's point of view. Now, as we have said that in mechanism design, the mechanism designer or the planner also has an objective. Without objective, we don't define a mechanism. So how can we actually mathematically capture that objective? And this is essentially captured through the social choice function, or SCF for short. So what does it mean? That if the agents had these types, theta 1, theta 2, and so on, then what outcome we should have taken. So therefore, this social choice function is nothing but a mapping from this Cartesian products of all capital theta i's. So when each of these players have actually choosing their own theta i's, so their own types, then in that state of this game, or in that state of that world, the social choice function should pick one specific outcome. So what is an example? So let's say in voting, when you are talking about elections, so each of these theta i's are nothing but different preferences. So theta i's are those examples, let's say B, A, C for player I, and similarly could be different preference orders for different players. We want a certain desirable thing to happen when we are selecting the winner. So for instance, that desirable property could be that if there exists a candidate who beats everyone else in pairwise contests. So let's say we are looking about only B and C, and we are looking at how many people have actually voted B over C and how many people have actually voted C over B. If B over C, this number of people who have voted B over C is larger than those who have voted C over B, then we will call that this B is beating C in pairwise election. If there exists a candidate which does this for every other candidate, then we should definitely output that as a winner. So that could be one desirable outcome. So we can actually put certain restrictions or constraints on the social choice function. So this could be a good social choice function. Similarly, you can think of a different thing that if this was, so suppose B over A over C, or maybe just the topmost candidate. So B was the topmost candidate. I don't really care about the ordering over the rest of the candidates for all these voters, but the topmost one is always going to be B. Then the social choice function should output B, because that is most preferred, unanimously preferred by all the agents. So therefore that should be an outcome. So that could also be a desirable property. So you can define different kinds of desirable properties, and that is what social choice function is. So similarly, this is the example from the ordinal world, but in the cardinal world you can think of a public project choice. So suppose we are choosing one of these projects, and where this theta is just giving you some real number. So theta I is nothing but whichever public project you choose. So this X could be set of all public projects, building a bridge, building a public park or museum, whatever. So that gives you a certain amount of happiness or satisfaction whenever you, if you are agent I. So that is captured by this function theta I, which is nothing but its type. So theta IA is nothing but the value of agent I for that public project A. Now what you are doing as the mechanism designer or the social choice function, the desirable property is that you will take the sum of all the agents valuations, and you will pick that public project which maximizes this sum. Quite fair. I mean, you look at all the agents, and if you are building a museum, then you look at how much satisfaction it gives to all the players, the sum of that. Or if you are building a public park or a bridge, depending on that, you will pick that one which maximizes the sum of the values. Now here is the most vital question, that all these types are essentially private information of all these agents. So we definitely have to ensure that we need to create a game such that this f theta, the desirable objective, emerges as an outcome of an equilibrium. We have already defined different kinds of equilibrium, and we'll reiterate some of those in this context. But we definitely need to design a game where this f theta, this socially desirable outcome, should emerge as an outcome. And for doing that in an equilibrium, we need these mechanisms, and that is exactly what we are going to discuss. So let me formally define it, define what is known as an indirect mechanism. We'll also come back to the direct mechanism very soon. So an indirect mechanism is a collection of message spaces and a decision rule. So the message space of player I is given by mi, so m1 to mn for each of these n players are the message spaces. You can imagine, I can give a kind of an analogous example. So imagine that that there are in the railway reservation system, there are different classes and there are different prices for each of these classes. Now I don't know what are the types of these agents are. So maybe the agent's value, so they have a value for the class that they are traveling, and they also have a budget constraint. Beyond a certain point they cannot really purchase those tickets. Based on that, they are choosing one of these classes. So the choice of the classes are the message space. So they can only indicate that which class they want to choose, and that is constituting the message space. And this is a kind of a derived information from their own type. So you are not really asking how much they value each of these classes, or what is their comfort level that they are looking for, and what are their budgets to travel in this train. You are just asking them to purchase a ticket from the available set of classes. So this is one analogous example of how you can think about this message spaces. So it's not exactly the same as their types. So types could be those basic information that I have discussed. Don't connect it with anything beyond that. Maybe the railways is not running a mechanism, but I'm trying to give that example just to give you a flavor of what a message space should mean and how you can think about it. Now, once each of these agents have actually chosen their message, so in this case, each of these agents are picking something from this message space. So they have already picked their choices of the classes of travel. And then there is a decision rule named G, which will take all these messages together and pop out one of the outcomes. And this will be the same outcome space as we have defined before. That is the maybe the decision could be like how many classes, so how many coaches of a specific class should be added, and so on. Now that is an indirect mechanism. It is indirect because you are not directly dealing with their types, rather you are dealing with their message spaces. A direct mechanism will be the same as above, where this message space is directly their type set. So instead of asking them for their messages, you are just asking them for their types. And also the decision rule is nothing but the social choice function itself. So whatever you are trying to achieve using this mechanism, you are just giving that as the decision rule. So in that case, all these MIs will be replaced by theta i's, and the G will be replaced by F, and that will be the direct mechanism. So here is a schematic diagram. So G is the rule that you have chosen, and all of this M1 to Mn. So M1 is belonging to capital M1. So each of these players have been given this message spaces, and they are picking some messages. And once everyone has picked their messages, G operates on them and then gives out a specific outcome which lives in that space, capital X. So this particular kind of a indirect mechanism is not very commonplace. We don't really deal with this kind of mechanisms, this kind of indirect mechanisms that much. It is because a result that we'll show very soon, known as the revelation principle, which actually says that you don't really need to look at the indirect mechanisms. If there exists an indirect mechanism, then we'll always have a direct mechanism. But please wait for that. We'll come back to that result very soon. Now, we have already defined the weakly dominant strategies in the game theory part of this course. So in this context, let us just define it as we use it for the mechanism design, and we will definitely see that there is a certain change, very minor, but there is a slight change in the definition of this weak dominance. So in this mechanism, we say that a message Mi is weakly dominant for player I at theta I. If you look at this thing, so you know that the utilities are defined over outcome and its own type. So we remember that UI is nothing but the mapping from X cross capital theta I. This is for independent private valuation to R. So therefore, this X outcome we are going to choose, and we are going to choose based on what these agents have chosen as their messages. So suppose agent I has chosen its message Mi, and other players have chosen some M minus I tilde, something. And we said that this Mi is weakly dominant if it dominates for any other message of the same player. So if the player instead chooses Mi prime, then this utility will never be larger than the utility that it gets when it picks the message Mi under this type theta. And this should happen for all M minus I tildes. So no matter what messages the other players are choosing, this inequality will get satisfied, and it should also get satisfied for all Mi prime. Now, what is the difference between the weakly dominant strategy that we have defined? In the weakly dominant strategy, we have also defined something like a strict dominance. strict inequality to be satisfied for some m minus I tilde. That is no longer true in this definition. The purpose, so we have actually weakened that definition. That was a more strict definition. The reason being that in this kind of a situation, the space of mechanisms that we can find is a little larger. And also, whenever we are talking about optimization, it is much difficult to handle strict inequalities. So if we are trying to design a mechanism and write all these constraints, this weakly dominant constraints as the constraint set, then we'll not be able to solve those kind of optimization problems. And that is one of the major reasons why we actually migrate to this weaker definition of weakly dominant strategy. In this module and also in the later part of this course, we will define certain things based on the cardinal preferences. So here you have already seen that I have used this utility definition, which is a cardinal utility definition. But you can also cast the same definition for ordinal preferences. So the above inequality. So here remember that this is an outcome. How you can write that this outcome is more preferred than this outcome under a specific type theta I is by writing this. So if you are choosing mi, then the outcome that you are getting is more preferred than the outcome if you are choosing mi prime as your message. And then also we will be calling that as weakly dominant. Now that we have defined this weak dominance, it is the right time to say how we are going to implement a social choice function. So we are going to use this term implementation. So we are going to say that a social choice function f is implemented in dominant strategies, of course in weakly dominant strategies, by this message, by this mechanism, indirect mechanism m1 to mn, g, if two things happen. So there exists some message mappings. You can think of these SIs as strategies that if you have a specific type, then you choose a specific message. So for instance, if your price to performance or comfort to budget ratio has a specific form, then that is your type. Then you choose to purchase ticket of a specific class. And if that is your strategy, so there exists such kind of strategies such that this SI theta I is a dominant strategy for agent I at that theta I, and this should hold for all theta I in capital theta and for all players. So you can actually expand out all this. What do we mean by this dominant strategy? SI theta I is essentially a dominant strategy for that player I. So what it means is that this weakly dominant strategy, as we have said, that it's a most predictable outcome. So you are expected to choose those SI theta I's in an equilibrium, in a weakly dominant strategy equilibrium. And the second condition says that in that dominant strategy equilibrium, weakly dominant strategy equilibrium, you actually implement the objective that you wanted to satisfy. So if the type profile was theta and each of these agents had chosen S1 theta 1, S2 theta 2 up to Sn theta n, then this rule G would have mapped that to be exactly equal to the f of theta. So in the equilibrium, you are actually implementing the social choice function, and that is exactly what it means. So you are implementing. So the first condition is just telling you that there exists such kind of strategies, which is a weakly dominant strategy equilibrium, and in that weakly dominant strategy equilibrium, you satisfy whatever you wanted to satisfy. And that is exactly the meaning of implementation. Now we are going to call this an indirect implementation because we are using an indirect mechanism as we have defined here. We are going to call that the social choice function f is a dominant strategy implementable by this indirect mechanism m1 to mn, g. Now you can also talk about the direct mechanism. So we know that in the direct mechanism, the message space itself is theta I, and the decision rule is the social choice function itself. This particular implementation has a very specific name. It's called the dominant strategy incentive compatible. if this inequality holds, that whenever you are reporting, or you are picking that message which is exactly equal to your type, whenever you are revealing that type in a truthful way, then the utility that you are going to get is at least as much as the utility by misreporting your type. So that is exactly what this terms we will be using very often. You can see already that we are sort of going towards truthfulness. So the truthfulness itself is saying that if you have a type theta I, so this second term in this tuple is essentially the true type. So if your true type is theta I and you are revealing your type to be theta I, then you get the utility which will not be surpassed by any other utility when you are when your true type is theta I and you are reporting something like theta I prime. And if this inequality holds for all theta I prime, and theta minus I tilde, so that is why it is dominant strategy, because other players might not be truthful as well, but as an agent I, your best response will be to report theta I truthfully. And if it holds for all agents, then we are going to call that this direct mechanism is essentially a dominant strategy incentive compatible. So to find if that social choice function is dominant strategy implementable, we essentially need to search over all possible indirect mechanisms. So that is one difficult part, that if we go for the indirect implementation, then this spaces could be very arbitrary and large. We do not really know whether there exists any mechanism. So if we could not find any indirect mechanism, does not mean that it is not dominant strategy implementable. But luckily we have a result, as we said, the revelation principle, which reduces this search space, which says that if you have a dominant strategy implementable mechanism, then you will always have a dominant strategy incentive compatible mechanism, which we are going to discuss in the next module.